In the previous exercise, we calculated the forward kinematics of this very simple robot. And the idea of the forward kinematics is that I give you like alpha and beta, and you give me the position and the orientation of the n effector. Inverse kinematics tries to do the opposite thing. I give you the position and the orientation of the n effector, and you give me um, the values of the joints that will fulfill this. It's important to know that not every position and angle is going to have a solution. Imagine, for example, that I have like a one robot with two links, and each of them is 1 meter, and I say give me like the angles of the joints if I want to go to the position 100, 100. So this is impossible. Now, if my robot has 1 meter links, it's never going to get to 100. So yeah, it's impossible to know that. Sorry, it's important to know that not every position is possible, but for those ones that are possible, in the case of the simple two-joint planar robot, it's actually very, very easy to calculate. So another idea, of this exercise is going to be like, if I give you x and y and theta, can you provide me alpha and beta? So to provide that, to build an intuition, imagine that there was only one link, that our robot was just L1. And the task then would be to find alpha if I give you x and y. This is actually very simple, no? Like just with sinus and cosinus, I can calculate it. I hope you can see this with basic trigonometry, that cosinus is going to give me like the continuous to the angle. Sinus is going to give me the opposing line to the angle, which is going to be y, and the continuous is going to be x. So, very simple, I can get the solution. The problem I have here is that, this is actually, problems like this are actually going to give me two different solutions depending on if the cosinus is going to be positive or negative. So imagine, for example, that you have like a robot like this one, and your objective is for the robot to get to this position. So you can actually get the robot to this position through two possible configurations, the one that you can see in black and the one that you can see in gray. So it's important to note that both of them are going to be possible solutions. So given a desired XY location for your n effector, there might be like a multitude of different solutions. In the case of a robot with two links, there is going to be two solutions, but in the case of robots with 6 axes, the number of solutions, it's going to be much, much higher. Anyway, so if we remember from before, from forward kinematics, we can calculate x. So given alpha and beta, we can very easily calculate x, we can very easily calculate y, and we can very easily calculate theta. So the question is, can we do, given x, y, and theta, can we actually obtain alpha and beta? And in principle, this is a bit difficult, to do manually, because as it says here, there will be two additional solutions and times to the 6th power. But the thing is that we are speaking about robotics, and as I'm saying here, not only do we care about x and y, but we also care about theta. And the fact that we are forcing a possible orientation makes the solution much, much easier. Because what we are going to have is a transformation matrix like this one. It's going to be like an angle of the n effector theta, which is going to be the orientation, and then the position x and y of the n effector. And if we remember, if we remember what I was doing before, so if you remember the f of the forward kinematics, which is exactly like this one. So this is the matrix, the transformation matrix of forward kinematics, and this is our desired pose. So we can actually associate one with the other, and we can see that if we associate one with the other, we can very simple solve this equation. So for example, if we just go like cells by cells in the matrix, for example, we know that cosinus of theta is going to be the same as cosinus of alpha and beta, which is that you can see here. So cosinus of theta is going to be equal to cosinus of alpha and beta. And then I can very easily see that x, is going to be equals to this thing here. And I can also see that y is going to be equal to this thing here. So basically, given theta, x, and y, and making the association between the forward kinematics and our desired pose, we can actually isolate the three parameters into these very simple equations. So this is the same as I was explaining just before, like cosinus of theta is equal to cosinus of alpha plus beta, x is equals this, y is equals this, which remember comes from here. So just doing, some basic maths, for example, I can remove cosinus from here and from here because it's in both sides, and then I get that theta is equal to alpha plus beta, which is, quite good. Which is actually the same as we were doing before. So before we're also saying this, and this is going to make our life very easy. So this is the equation of forward kinematics, and this is going to make our life very easy because we are going to know theta by default. So the only thing we are going to need is to actually either calculate alpha or beta, and then we can isolate one or the other. So for example, if we obtain alpha, so we know that theta minus alpha is going to be equal to beta. So actually, we only need to calculate one of the angles, and the other one is going to be automatically solved. So as I was saying, I can remove one, I can remove the cosinus, and then it gets super simple. And then I can pick to either work with x or y. Let's say I'm going to solve with x. So the only thing I need to do here is to isolate, this cosinus here. So basically what I'm doing here, so if we compare like this equation with this equation, is basically isolating this for cosinus of alpha. So I'm sending this on the other side, in the case it is it is reversing. So I'm basically saying like here is doing cosinus of alpha beta L2, but it can also be like cosinus of alpha beta L2 minus x. So I just move this to the other way, and then I can the L1, which is multiplying, now I can actually send it dividing, and this is going to be equal to the cosinus of alpha. And remember that if we have a cosinus of alpha, its inverse operation is going to be arc cos. So then I can say that alpha is equal to arc cos of all this thing here. And then what is very interesting is that, as I said before, theta is equal alpha plus beta. I don't know alpha plus beta because this is what I'm trying to find out. So in theory I cannot calculate this, but I can just replace this with theta, as you can see here. Now it says that alpha plus beta replace with theta, which is one of the arguments that I'm giving to solve, because I'm telling you, like theta is 45 degrees, x is 2, and y is 3 or whatever. So I'm actually giving you this. So thanks to this, I can replace one with the other, which means that I have like the complete solution here for alpha. So basically, the solution of alpha is going to be the arc cosinus of the cosinus of theta multiplied by L2 minus x divided by L1. And this equation here is also another solution for alpha, but in this case is using the sinus. So it's actually the same as before. So you can either, solve one or the other. And once you obtain alpha, as I was saying before, you know that beta is equal to theta minus alpha. So it's, it's straightforward to calculate beta. So I hope you see that in the case of the 2D planar robot, if I'm giving you x, if I'm giving you y, and if I'm giving you theta, calculating alpha and beta is, is very straightforward, because this value is given, is the second link, this value is given, the first link, this value is given, which is the position x of the n effector, and this value theta is also given, so I only need to put these values here, and it gives me the position of alpha. So yeah, I hope you can see that it's very, very easy to calculate. The main thing that you need to have in mind, as I was saying in another slide, is that you need to consider always that the cosinus is going to be positive and negative. So when you solve the inverse kinematics, you are always going to have two solutions. So just remember that.